Welcome to Delta Computer Systems webinar series. Today, Motion Product Manager Jacob Passo is going to be showing more in-depth techniques and tips for RMC Tools user programs. Thank you for taking some time to be with us today. A recording of today's presentation will be available in a number of places after the session, and we'll cover where to find those places at the end of today's broadcast. Questions are encouraged during the session. Please use the chat window to enter your questions, and we will try and do our best to answer as many during the presentation as we can. And now I'd like to hand it to Jacob Passo to begin. Welcome, Jacob.
Thank you, AJ. Hello, everyone. Today we're going to talk about advanced user programs. And I'm sure many of you are familiar with the fact that this is a huge topic. Today we're going to focus a lot on the architecture of user programs. There's many things we won't cover. Hopefully cover those in later webinars. First of all, I want to say that user programs in the RMC gives a lot of power. The combination of the looping and branching plus the expressions to do calculations gives power to handle any application, lots and lots of applications. I think many of you are familiar with the fact that we can do simple motion user programs. We can do complex motion sequences. We can do all kinds of combinations of moves and gears and sine waves and curves and calculations, plus some very complex motion that requires user programs. So I just want to show briefly a few examples of some advanced applications. Here is a little video of a 6-degree of freedom system that can be done using user programs. This particular one is kind of a cutesy that was shown at a trade show in India. Little teddy bear going back and forth. And of course, this 6-degree freedom system can move anywhere you want to in 6 degrees. If we look at the project from that, we see here that we have in the programming, user programs, one program to set up a lot of calculations, a whole bunch of sine and cosine calculations, and then another program that does a lot of initial calculations, a whole lot of math going on here. Whenever we do with kinematics, we have lots of math. And we move to initial positions here, and then later on, we can continuously do these calculations, and these calculate a velocity, acceleration, and position for each point. And then we do time move absolutes to go to these points that are being streamed to the RMC, and it continues forever. Another application we have is platen leveling. If I bring out a little video here, this is a video of a cylinder with a totally flexible platen, and it uses custom feedback to calculate the force of one cylinder plus the other one, and calculates the total force, and while keeping them level, applies a set force on this block. Uses cascading outer loops, and it requires to use a program in order to do that. We'll look very briefly at this user program just to get an idea of the complexity of it. Here we have custom feedback where we're calculating the average position and the sum of the forces for a total force. We have a user program that sets up the gearing relationships between the cascaded outer loop and the inner loop. Not necessarily so long and complex, but conceptually rather difficult. And then once we have it set up, we do a typical motion sequence, few moves, we enter pressure, force control, ramp it up and down, and so on. Another example we have, unfortunately, I wasn't able to find a picture of it. It's a bit old now, I guess. Couldn't find a video on it. Is a synchronized open loop system where we have some cylinders compressing a hay bale, and they have to give everything they got. So regular closed loop doesn't work so well. So we came up with this program where we do open loop to all the axes, and then we make our own custom PID inside of an expression and user program to modulate the voltage going to the cylinders that are furthest ahead in the system, and it ends up synchronizing them basically in kind of an open loop fashion. So just all kinds of power that we have in these user programs. Another one is adaptive amplitude control. When we're doing high frequency sine waves, it's not possible for the actual position to follow the target. So we do a modified method where we just over time adjust the amplitude to get to where we need to be. That example is also rather complex. If we look at that with the programs here, let's see, we have this one here maybe. We have user program where it's doing a sine wave, and then we have an expression that's looking at the max and min, and then adapting the amplitude of the commanded sine wave so that the actual gets to where it needs to be. Plenty of calculations here that, of course, are only possible when we do it inside a user program. So those are just briefly some examples of the power that we have. So I want to talk now a little bit about the motion programming architecture. When we have a project that we want to do on a machine, one of the first questions that we encounter is, do I do the motion sequencing in the RMC or in the PLC? In the RMC, we have the user programs that we can create and run, but you can also, from a PLC, send motion commands to the RMC itself. So you can do all your logic in the PLC and send the commands to the RMC, depending on the situation. Some situations require user programs, of course, but in many situations on a regular machine, we can choose. So some advantages to the RMC is that it responds faster. It responds at the loop time of the controller, such as 1 millisecond. In that user program, it can look for conditions, whether it's reached a position or it finished a move or some error occurred, and it responds immediately. If we're doing in the PLC, we're limited to the communication rate. And nowadays, communication rates can be very fast. We can go down to 1 or 2 milliseconds on Ethernet IP or Profinet, for example. Modbus TCP, if you have a good network and high power PLC and so on, it can be pretty fast. But you generally, if you're going fast, now you're eating up some bandwidth on your network. You have to keep that in mind. If we do the motion in the RMC, it offloads the PLC, and often customers have reported they can get away with using a less expensive PLC and save a little money on the application. The RMC is also designed for motion sequences. We just got some feedback within the past couple of days from a customer who compared the RMC to another motion controller that used standard 61131, the IC programming languages, and they really liked the RMC's motion sequences. The user programs are designed for the motion sequences. So a PLC is a great machine controller. The RMC is a great motion controller. So if you have motion that's kind of related more to machine control logic, you may want to do that in the PLC. But for a lot of motion sequences, the RMC is well designed for that. And of course, certain applications must be done in the RMC. Whenever we're talking about custom feedback, where we're getting feedback calculations every loop time of the controller, that typically has to be done in the RMC. And some of the examples I just showed you with all the complex calculations that need to be done immediately, they of course need to be done in the RMC. Some reasons to do it in the PLC is if the user prefers the PLC. Some places have their electricians or maintenance personnel or whoever trained up in the PLC, but aren't necessarily so willing to learn the RMC. In that case, well, if the PLC sends commands to the RMC, that's probably just fine. Being the PLC is a very good machine controller, there's also certain types of flexibility that the PLC may be better at. We'll go through one of those examples a bit later in the webinar. And the RMC has had some improvements in certain types of flexibility, but that difference will always remain. The PLC will be a better machine controller, and that may play into the decision. So in motion programming architecture, one of the first things we do is we take the motion required and divide it into sequences. So generally, we simply just use the logical, chronological flow of motion, and we make it into user programs. Now we have some choices here. We can make one really long program, or we can take that sequence and divide it into some shorter ones, and the PLC can start them at the right time. This is totally your choice. I want to really emphasize that anytime programming is involved, there's usually many ways to do the same thing. So we're just going to go through some basics, some classic methods here. One thing that may be a fallacy sometimes is try to have one user program per axis. Sometimes that works, sometimes that doesn't. Generally, you want to look at what the machine does, what axes need to work together, need to work consecutively, and so on, and we stick those into one user program. It's very common to have some larger user programs for the main sequences and then several short ones for small operations, maybe jogging or maybe halting or maybe adjusting calibration values or something. That's a very typical thing that we see. So I want to show a little example, just a completely made up example that will illustrate some of these concepts. So consider a system here where we have a machine with 3 cylinders that can move in position and force control, and at sometimes they can work independently, and at other times they work together with each other. So maybe there's some parts that they're pressing, and they often can work independently, and they have very high productivity that way, but occasionally they have a long part that needs to be pressed with all the cylinders together. This machine is flexible enough to do both of those. And we do actually have a customer who's done a very similar application like this in real life. Made a real good use of the machine, being able to do long parts, but then high productivity for the small parts. So occasionally we want these cylinders to move independently, do a pressing operation where it closes the press, builds pressure, dwells a little bit, and then decompresses and then moves back. A very classic press cycle. And we want them to do it independently and then sometimes together. So if we look at an example project for that, right here we see we have an RMC 200 and it has a few modules on it, and we have defined a few axes, 3 axes with position, force control. We can see which inputs and outputs they're connected to here, and I'm live with this controller. The axes here are in simulate mode. And we can see that I have come up with some user programs here. We have a press main program for press 0, so that's the first axis, axis 0. And then we have some jog open and jog close and jog stop for that same axis. And we repeated the same for the next axis. So we have press 1 main, that's the main pressing cycle. And then the smaller programs for jogging, close and stop, and the same for the third one. Then we have another program that does it for all of them together. And then we have a program that halts all the axes if need be, and then one for some background operations. So if I look at this press 0 jog open, all that is a move command to the press open position. Look at the close, it's a move command to 0, which is the close position on this particular press, and then to jog stop, where we stop. So the jogging function here from the PLC, it can start one of these user programs to open or close, and then when it wants to stop the jog, it sends a jog stop user program, and that will send a stop command to the axis. So probably an HMI is hooked to the PLC, and when you press the HMI, it sends data to the PLC, and the PLC sends the data to the RMC. Very typical way of doing it. You can also have an HMI connected directly to the RMC to start and stop these user programs for jogging. Now the main program here, we've divided it up into a sequence here. I think, let's see, I might have a little error here. I shouldn't have that one and I shouldn't have that one. We'll talk about that later. So ignore those for the moment. So this sequence here, just kind of made up sequence. It would be great to show some of our customers' projects, but generally that's not polite to share things like that. We get some really good user programs in here sometimes from customers. But this one does a fast close, a slow close, a fast close speed, and then it slows down to a slow close speed, does dwell, and then ramps up slowly from that. So we see here quickly, does a move absolute command. Once it hits the slowdown point, moves at a slower speed. Then once our force starts increasing past some value, we enter pressure force control until we get a set point. Once we have reached that force, then we go to the next step and do a dwell. After the dwell, we ramp the force to 0, so decompression. And once that's complete, then we move the press back to its open position. So classic flow of a user program. This one is, of course, reasonably simple. Generally in real life, you're going to have all kinds of other things that come in and make it a little bit more complex. But we've done the same thing here for press 0 and press 1, similar program, press 2, and press all, where it does this for all of the axes identically. So we have a move command, it's commanding all 3 axes, and then it's waiting for the axes to reach a slowdown point. Commands them all at slower speed, enters pressure force for all the axes, dwells, decompresses them, and then moves back. So these are the main user programs we have. Generally, you need some ancillary programs like halt all axes. If something goes haywire, we need something that's going to stop them all. In this example, we just did a direct output halt. Typically, there might be something else going on as well, turning off some enable signals or power to HPU or whatever. Although sometimes the PLC controls those kind of things directly. We have a background task here that just does some continuous calculations that we may need. Talk a little bit about that later. But basically, we've kind of divided up the main motion sequences here. And again, this is a fairly simple example, but kind of covers the main ideas. But once we have created those user programs, now we need to assign them to tasks. So remember that a task is something that can run one user program at a time. And in RMC, we have a certain set number of tasks. We can kind of visualize them if we go to the program triggers here, where we can start them as we wish. But you don't have to use the program triggers to start tasks at all. You can start them with a command, that's just fine. But we can kind of visualize them here. And in the program properties, if I right click, choose properties, we can choose the number of tasks. And each RMC has a maximum number. The 75 has 4. The RMC 150, I think, has 10. RMC 200 has 32 tasks, I believe. So this happens to be an RMC 200. I can increase the task beyond 4 quite a bit if I wish. But for now, we just have 4 tasks. That'll be fine. So we need to know how to divide the user programs among the tasks. So the basic guidelines are that user programs that cannot run simultaneously, you assign them to the same task. So for example, on task 0, press 0 main, that does our main motion pressing cycle on the first axis. But if I'm jogging that axis, I don't want those to run at the same time. So I can make sure those will run on the same task. So if I happen to be jogging and then I start this main cycle, it will automatically stop this user program that was running, the jogging program, and start running on the main. I wouldn't want those 2 user programs running at the same time because that would be very confusing. Next, any programs that can run simultaneously, I assign to different tasks. So remember those cylinders that we have pressing. When they're running independently, they can run totally independently. So I can have a pressing cycle going on the first one and the second one and the third one all at the same time. So I do the press 0 programs on task 0. And then on task 1, I do the press 1 programs so that these can run at the same time. Task 1 is take care of its thing. Task 0, take care of its thing. And task 2, taking care of its thing on the other one. And that can be completely independently controlled. We can have completely different personnel feeding in material into each system, or of course maybe an automated feeder or whatever. So we put those on different tasks. Now we have the other program, the press all main, and that one uses all three axes. So these things that are running at different tasks, well, when we run press all main, we don't want the press 2 program to be running. But of course, we can't put press all main on all tasks to keep them running from the same. So we're gonna have to deal with that differently. So in the press all main, we can run it on maybe task 0 just because. And when we start it, of course, it will stop anything that's running on task 0. But in that program, press all main, I should probably at the beginning here make sure that it stops the other tasks. So I'll add another step here, and I think I need to probably move this down. We'll copy this, paste that. We can probably just do an immediate there. Let's see, add a command here, and we can do a stop task command, so that we'll want to stop what's running on those other tasks. Doesn't matter which axis we send this command to. And we can only do one stop task command per step. So I'll do that here. And then we'll stop task 2. So when I run the press all main that's running all three axes, I want to make sure those other tasks that are also controlling those axes stop. So we use stop task for that, task 1, and stop task for task 2. And then we jump to the next programs here. And I made those edits, should be able to download that. A few other items of note here is that in the user program properties, you can specify which tasks a user program can run on. So in the programming properties, right-click, choose properties. I can choose here on the general, no, sorry, that's on the individual program. So if we do press 0 main, properties on that, and tasks, I can tell it which task it's allowed to run on. So if anything tries to run it on a different task, it'll give an error and won't actually run. So that one I've set to run on task 0, and press 1 main. If I go to properties, I've set it that it can run on task 1, and press 2 main. If I look at that, I've set it so that it can run on task, whoops, we want to change that to 2. There, much better. Okay, download that change. And let's see, press all main. See if I did that. Okay, task 0 there, that's fine. So we can run this. Well, actually, I think I have a couple other things to notice here. If a continuously running user program is required, dedicate a task just for that. So we have here this background program. It's calculating some things. It's calculating the total force of all the axes, and that it doesn't have to run all the time, but it has to run when we're doing the press all main. So we might as well just have it run all the time. And then we're also calculating the skew between the axes. We're also doing a heartbeat here that updates a value every half second, and the PLC can read that value. And as long as that value is changing, the PLC knows the RMC is alive and user programs are running. And so that we want to run all the time. So we can see in the program triggers on task 3, I'm running that background user program here. And so task 3 is just totally dedicated for that. I'm not going to run anything else if I need to run this all the time. So let's just look at an example of running this. If I look at the plots, axis 0, let's see, I have actually those, where's my program triggers? I have the program triggers set up so we can run these things. We can also send a start task command. We can try either way here. We'll just do a start task command for now and run press 0 main. And we should be able to see that that runs here. And we'll stop in a bit and describe what happens. So we see here the red line is the position. Started at 10, fully open, and then went down here at a speed. And here it slowed down. You can see the blue line here was a speed. It was pretty fast, negative, and then it slowed down. And then right here, we enter pressure force. If we zoom in, see where the yellow target force jumps here. That means it's now in force control, and it ramps the force down. Look at the force. Let's see, that goes from 0 to negative 2,000 pounds right down there. And then that we dwell down there in force control for, looks like from here to there, it's about 2 seconds. And then the force ramps up, gray line, to 0. Once that happens, now the position, we move that up to fully open on the press. You'll see in the plot here that we have this gray line here. That's the task 0 current program and step. So that tells me which step the program, the task 0 is currently on. We can see that it changes here, 0, 2, 3, so on. It's actually giving me some funny values. Maybe we'll run that again, see if it shows up a little bit better. We'll run again. There, it showed a little bit better. It had started off in a goofy state. But now we can see this gray line. This I added to the plot so we can tell in the plot when it's transitioning from step to step. So the gray line, we see it changes here. So it starts the first step, stays on that one, switches the next step here, and then here switches, there switches, there switches, here switches, and there switches. So I can follow along in the user programs on what the plot did. It's really good for troubleshooting. So generally in the plots, you want to add that. If we go into the plot templates, to add that, we go to new quantity. Of course, you have to choose a custom plot here to have the new quantity. We go to new quantity, tasks, task 0, and current program step will add that for the task into the step. Of course, it won't let me, or into the plot. It won't let me here because I already have it, but that's where you find it. And of course, if I ran the all axes position force, let's go run that one. We'll see similar. So press all main. That should do all the axes together. Looks like we're moving. They're moving down. Stay down there. Ramp up. Similar type of a thing. Right here, I don't have the user program steps on there, but I could add those to the plot and be able to tell that. So, simple example of organizing those user programs and running them. Let's see. A little bit more about the continuously running user program. These are for calculations that must continuously be performed. Custom feedback's a classic. Updating status. So sometimes you might want to aggregate a lot of different values in the RMC and send it back to the PLC and say that, hey, this is all right, that's all right, this isn't, that isn't. So sometimes you might have some logic that aggregates those together and puts in a nice status value for the PLC to read. You want to do that all the time. A heartbeat as well. We'll look a little bit how I did that. Just a second here. So if we go to the background user program, we have the step 0, it just has to initialize a value. And then step 1, we're calculating the status information right here. So that's always updating the force and skew. And we just want that always to run. So I initially started with that, and that's all I had. And then I wanted to add this heartbeat. And that does a timer where I capture the system milliseconds in the RMC. And notice before I'd stored the system milliseconds in this timer. So the timer took a snapshot of that and stored it. And the system milliseconds, of course, continues running because it's just calculating how many milliseconds have passed. So as that keeps going, that'll become bigger and bigger than the snapshot I took. And eventually when that's greater than 500 milliseconds, which is half a second, then I reset the timer value to this, and I add one to a heartbeat variable. And this heartbeat variable is just simply defined in the variable table. Let's go look at that here in the variable table. I think I have it at the bottom here. And the PLC just reads that heartbeat value. And it's, of course, going to be changing every half second according to this. Now, you'll notice in the expression that I have an if-then-else for this. Another way to do an if-then-else is that in the link type, I actually do a conditional jump and have a link condition. And if it's true, then I have a step on there that I do something. But in a continuously running user program, if I jump to another step, well, I'm not going to continuously be evaluating this expression here. So generally, in a continuously running user program where I have to update values constantly, I don't want to use a conditional jump link type. I just want to use a jump and repeat and don't have any more steps. So I generally only have one step in this kind of user program unless I need something to initialize some values like I did here. So normally, you have to add if-then-elses in the expression to do all that logic where if this happens, then that happens all in one step. It can be a little bit challenging sometimes doing one step. Sometimes we end up doing a state machine inside that step. If you have plenty of tasks, you can actually have multiple programs like this. So maybe one is running all the time, and another one, it doesn't have to run all the time, and so you can do those if-then-elses and kind of take your merry time. So you generally have a choice of which way you can do it like this. Another option is to have, instead of the PLC starting user programs, you can have one user program in the RMC managing other user programs. So I want to show you a little example. We have a, well, let's see. Looks like I don't have that video up. Let's see just a second. Okay, so here we have a 12-axis motion demo that we made for the RMC 200, and it does various motions back and forth. It starts out by zeroing each axis one at a time, and it moves it, and then moves them in sinusoidal fashion. You'll see the left side is slower frequency and the right side is higher frequency. It varies in between, and it makes this really cool pattern that ends up looking like a sine wave itself, and runs that for a little bit. And there's a few different sections here that we opted, instead of having one big long user program, we did several smaller user programs, and then there was one user program that managed them. So you'll see at the end they come in a line, and then it does this little bow. So in order to make it very flexible, we actually had one user program managing the rest. And let me see if I can find that example here. Okay, so we have some user programs, and we have a sine move. We had a couple different versions of them. Adjust frequency, and we have a move to midpoint, and we had a bow, and then we have a runtime program here that all it does is runs user programs. This is a pretty lousy example of user program because there's no comments telling you anything. The first comment should be that this task or this user program has run on task 1, and because it's starting these other tasks on task 0. So it tells this first task to run, or this first program, home all axis, to run on task 0. And then it has this variable, home complete. So I think this home all axis must set home complete is equal to true. Let's see if that's correct. Yeah, at the end here, this one says home complete. So it runs that. Once that variable is done, it runs to the next step, starts another user program on task 0, which moves to the midpoint, all of them. Then it waits and runs a task here, sine move 3, for a certain number of seconds, looks like. It uses a timer functionality. And then after that, it runs this move to mid-successive program. After that, it does that final bow. So this is an option where you can have a user program managing other user programs. instead of the PLC managing user programs. And of course, here we're using steps and commands. I've seen some customers who have had big, long expressions that do calculations for managing user programs. So that is certainly an option for how you architect your user program, is managing the other user programs by a single other user program. I don't see any questions in the question panel yet, but feel free to ask if you have any. One thing that comes up sometimes is dealing with a limited number of tasks. For example, RMC 75 only has 4 tasks. And sometimes people have a lot of motion sequences to do, and maybe some things that have to run simultaneously, and it can be a big challenge. But normally we're able to fit those if we just modify the programming a bit. And kind of the big thing is to consolidate multiple background tasks into one. So just as I mentioned, where we have in our main example here that we've been looking at, this background tasks, this user program that's dedicated on one task. If we can combine a lot of things into one step, then we generally make a more efficient program. One other item I want to talk about here is commanded axes using expressions. So instead of telling a user program to send a command to axis 0 or axis 1, we use an expression to programmatically define which axes we're sending it to. This creates flexibility in sending or not sending commands, because typically in any user program we have, let's go look at any random one here like this one, we tell it to send this command to axis 0. Well, there might be a situation where, depending on the logic, we might want to send this command to axis 0 and axis 1 and axis 2, or just axis 0, or we may want to send the command, or we may not want to send the command. And historically, that's where a PLC has had more flexibility than the RMC. But we have added a feature to the RMC that improves that. It's been in RMC for a while, so this isn't anything really new. We'll look at an example I have for that. Let's look at a video first. This is a little video here of a knee carriage. So we see here that we have a log. It gets fed onto this carriage here. And we'll see this knee here and here. They move in and out to move the log back and forth. And there's a third knee back here, but this is a short log, so it's not using that third knee. But if we have a longer log, it will use the third knee. So for right now, we're just using those two. We can see it gets it, the dogs lock it on, it moves it over here through a bandsaw, cuts off something, indexes forward, moves it backwards through the double-sided bandsaw and cuts it. And then now it rotates that. These dogs lock onto the log and moves it forward again and cuts it. So I specifically want to show a little bit about these knees here. You know, we have 1 knee, 2 knee, 3 knee. We could have one with 4 or 5 knees. And sometimes only 2 knees are commanded, sometimes 3, sometimes 4, sometimes 5. And to do that programming to decide how many knees is going to be commanded becomes very challenging sometimes. But we have in the RMC a method to make that very flexible, so it can be done inside the PLC or inside the RMC, and you don't necessarily need a PLC. So that example here, if we look at it, knee example, have used a program here, says move knees initial. So this is just a basic move on one of the knee axes. Do a move absolute to an axis, and we tell it to go to commanded position of axis 0. And let's say this was knee 3 or 4, that sometimes we want to command and sometimes not. So we have in the commanded axes box this use expression. If we choose it, instead of it telling that we use axis 0, it tells us that we use an expression, and this expression uses a D word. So let's go see, I have some variables defined here. A D word, we'll say command select axis 0. That defines which axes this command will be sent to. So if I look at the variable table, command select axis 0. I expand this D word as 32 bits. Bit 0 corresponds to axis 0, bit 1 to axis 1, bit 2 to axis 2, and so on. So in this word, if bit 0 is set, that means that command will be sent to axis 0. If bit 1 is set, it means it will be sent to axis 1. You can have multiple bits set at the same time to send them to multiple axes. So in my program, I just have to have some expression ahead of time that sets the bits properly, or my PLC can write to that variable and set the bits properly. So for this one, if I just am worried about axis 0, I would either have bit 0 set in this word or not. Now, if I expand that to more axes, let's say we have 4 knees in here, then I have different positions each knee needs to go to because the log is normally not totally straight, and we have to move each knee a little bit differently. So I have command position of axis 0 and axis 1 and axis 2 and axis 3. So each command can only be sent to that specific axis, not multiple ones. So I need multiple words here for deciding whether the command is going to get sent to the axis. So command select of axis 0, that's a variable, a D word, and if bit 0 is set, then we will send that command to axis 0. Same here, if this word has bit 0 set, we will send the command to axis 1. If this word has bit 0, if it has bit 1 set, we will send it to axis 1. And this one, if it has bit 2 set, we'll send it to axis 2. And this one here, if it has bit 3 set, we'll send it to axis 3. If it doesn't have bit 3 set, then it won't send it. And we won't worry about the other bits because we're not going to send this command to any other axis. So it's either whether bit 3 is set or not. But we need a little bit more than this. We can make it a little bit slicker. So if we expand this to a little bit more, where I start out with just one variable that's called axis command select. When we go to the variable table, I have it right here, and it actually gave names to these bits. Makes it a little bit easier. So bit 0 of axis 0, axis 1, axis 2, axis 3, and so on. So the PLC just writes to this word is all. It doesn't have to worry about these other ones. So it writes to this word, sets exactly which axes we're going to do, maybe 0, 1, 2, and 3 if it's using 3 knees. Then here we have an expression that looks at that. And if bit 0 is set, then it takes the command select axis 0 and sets bit 0 to be true. And it does that for all the other ones. So the PLC only wrote to this word, and this logic sets the other bits in those other words correctly, puts them over here, and then the commands get sent to the right axes. Now we need to wait for them to get into position. They should get into position at the same time because these are sync move absolutes that do the synchronizing move. And then we have some logic here that waits for the in position bit to turn on, but it only cares if that axis is currently selected or not. So this logic here is a little bit complicated, but if you actually study it, hopefully it's correct, and basically says if an axis has been selected for a command, then it considers whether in position bit is on. Once they're all on, then here we delay and then move back to 0. Just a simple example of that working. So the commanded axes and expressions can create some flexibility in sending commands. So if you're running into that kind of an issue with flexibility and thinking you do in the PLC, you might be able to do it in the RMC. A few more things, a little bit about variables. When you create variables, it's nice to organize them in groups by function. It can be helpful to use a common prefix based on their function, and you don't want to make the names too long. So if we look at our example that we've looked at mostly here, we've looked at the variable table. So I've grouped them by function. So the press 0 cycle, it has these variables here, and I prefix them by press 0. Makes it really easy to look for them and search for them. By the way, you can search for things if you go edit, find and replace, find all. I can look for, let's see, press 0 and we do a find all. And so now I can see them down here. It tells me where they are in the variable table, or where they are in the program triggers, or where they are in the program, whatever. So if I prefix them, it makes it a little bit easier to look for variables that have to do with a certain function. Generally, I like giving space between the different sections, makes it easier to see. And I try to make the variables descriptive and not too long, because sometimes in a user program, you may have a variable inside a box here. Let's see, we have it inside a box here. And if it's too long, it's hard to read. You can hover over and look at that. We generally get requests and sometimes make these boxes bigger, but it's not necessarily so simple, but we'll see what we can do about that in the future. In addition to the basics about variables, I want to talk a little about troubleshooting user programs. We already looked at seeing the current program and step in the plots, really good for troubleshooting. But we also have in the event log some good features there. If I look at my example, let's see if we can go online with that there. And we look at the event log. Right now it's being filtered. I'm going to reset that to defaults. And so the event log right now, it's just being flooded by information here. If I pause it, I see that it's coming from, let's see, task 3 transition. So it's what's running on task 3, background.1. So that's the background user program. And it's showing me all the calculations. So this task 3 is running background program, and that's flooding my event log, so I can't see other things. So I go to properties and tasks. In task 3, I'll turn those things off so it doesn't flood it. Now if I start running that and clear it, okay, so it's not flooding it anymore. Now if I run a sequence, like say press all main, now I can actually see in the event log what's going on. And I can see the commands, I can see where it started the task, and it says task 0 started, goes to press all main dot 0, so step 0 does something, goes to press all main step 1, and so on. And of course, these are just the basics of troubleshooting, but that together with the plots can generally help you figure out things. And last but not least is documentation. Use comments. Using comments is an especially good idea 5 years after you wrote the program and your customer called you back and you have no idea what you did, and all of a sudden it was a really good idea to have actually written comments beforehand, and we generally all forgot. But there are a few customers who generally remember, and that's really helpful. When you send to Delta for technical support, we can figure it out. When you yourself have to support it later, you can figure it out. A tip is to create a program that gives a project description. I want to show you here briefly a user program. Let's see if I can find it here. This is actually from a customer. I've kind of modified it to protect the innocent, so it's not possible to figure out where it came from. But this is by far the best documentation I've seen from any of our customers. And this is just one of the many user programs it was in, but it starts with description, some history, some versioning. Every step, there's a good, nice, clear description. It used capital letters, so it's very clear and visible to see what's going on. Inside the expression, lots of comments divided very nicely. They use labels on each step. If we continue down, we see it's very consistent that they have the documentation for this. And this is just a dream and delight to look in. It'd be much nicer to troubleshoot this kind of a user program rather than one that has no documentation. So just a little example of what is possible and recommended best practice. Let's see, just one moment here. My question bar kind of disappeared there. Okay. So today, this is all we had for the user programs, just basics about architecture and so on. There are a lot more topics that we could cover, and in future webinars, we will very likely cover those as well. Is there anybody who has any questions? Oh, a question about default access. No, I have not. I can talk about that a little bit. Another question is asking if the number of tasks is limited to the number of axes. No, the number of tasks is not necessarily limited to the number of axes. So if I look at my example here, on the programming, if I go to properties, well, let's see. We have 3 axes here and programming properties. I can increase this to the max that's allowed for that RMC, which I think was 32 for the RMC 200. Yep, that's the max. So I could have 32 tasks there. The RMC 150 is limited to 10, RMC 75 is limited to 4. And whether you have 1 axis or more on an RMC, you can have up to the max number of tasks regardless. And the question on default axis. Default axis is something I normally don't cover because it's very complicated, but we're talking about advanced things here, so we may as well. So if we see this press zero main, let's copy that and paste and make a new one. Let's see where that one ended up, right there. So if I open this, right now, I have sent these axes to commands to axis 0. I can choose default axis instead if I want to, and we can copy this and we can paste it to the other ones. I'm just going down to Control V on all these commands. And there we can do default axis. And we also have to change the link condition as well if we want to use default axis. So if I don't have a value inside the brackets here for axis, that means it's going to look at my default axis. Let's see, go here, change that one. So it's going to look at the default axis, and we can continue down, of course, and do this for all the other ones. Let's see, there aren't so many left. Maybe I can do those here real quickly. And on the last one, remove that. So now we have this user program set up to use a default axis. It's a little bit trickier because I'm using variables that are kind of set for a specific axis. But if we kind of don't worry about that for now, the default axis makes it possible to make one user program that can be run for any axis. So if we have a sequence that only involves a single axis, then this might be an option for us. The default axis takes on the value of the axis that the start task command was sent to. So if we send a command and I use axis 0 here to start it, then the default axis will be axis 0. Now, if I use this same thing here, same command, just put it on axis 1, same command, it's going to start the same user program on the same task, but I send it to axis 1, then that default axis will be 1. So now this user program, it will actually apply to axis 1. And I think in the program triggers, I'm not sure, I think if you start on task 0, the default axis will be axis 0, and start on task 1, the default will be axis 1. No, I'm not sure. Let's go look in the help topics here. If I look up default axis, we have a topic on it. Well, it's inside the task topic. So let's see. The default axis. When a task is started from program triggers, the default axis for the task left unchanged. On power up, the default axis for task N is axis N. Okay, so in the program triggers, the default axis will be the same as the task number. So if I go look at that one program again, I could have this program and I can operate it for axis 0 or for axis 1 or axis 2. And the cool thing is I only need one copy of the program, but I can have multiple instances of it running independently using the current axis for whatever task it's running on. It gets a little bit confusing, but we can also change the current axis. So I can go in expression and I can look at tasks, whatever task we're running on. I'll say current axis for the current task. I can actually set that to a value. So I can actually define what the default value is if I want. And of course, that will override what the default access was when the user program started. So again, this is a little bit complicated. I generally discourage customers from using the default access because it's easy to get confused. But I do know we have plenty of customers who are very advanced, and if they understand it solidly, by all means, go ahead and use it. It makes for some efficient user programs. But you know, if you have someone coming behind you that's maintaining the program, it might be a little bit easier if you do it an easier method. Let's see, another question here. Are the user program templates for different programming architectures, like a state machine? Not really. We haven't put out so much information about architectures. Kind of this webinar is kind of a little bit of the kind of first concerted effort for that. But that's a good idea. We should come up with some program templates. Like doing a state machine inside of expressions can get complicated. But if you have an example, that would help. So we'll hopefully put up an example on our forum. And another question, if we always want the task running, if the program needs to be running and waiting for a specific input, that's where we might want to do a state machine inside of that individual user program step. That can be useful for waiting for a specific input. And hopefully we can come up with an example of that. And let's see, mentions about you have to go to program properties and allow the program to run on multiple tasks. Yes, Norman, you are entirely correct. You normally are correct, Norman. So if I use the default access that I talked about here, the press 0 main copy, I need to go to its properties and allow it to be run on many tasks, any number of tasks at once. The default is this for any program, that I can only run at one task time. But if I want multiple instances of it, I want to be able to say it can run on any number of tasks at once. So yes, the default access, if I do it so I can run multiple instances, that is very important. Good catch. I'm glad you mentioned that. Any other questions? Okay, doesn't look like there are any questions. We thank you for today. And again, we'll probably be coming out with more information on user programs. I didn't go into very much detail on the expressions or user functions, and there are certainly other topics that we'll be covering in the future as well. So thank you very much and have a good day.
We really appreciate your attendance and interest. The webinar program exists for you, our users, and so we appreciate the interest that you've shown and appreciate you attending today. I wanted to mention, we said that there were a number of places you could get recordings afterwards. So here they are. If you visit deltamotion.com/education/webinars, just follow the links, through education, you will come to the webinars page. It will have the scheduled webinars coming up there. You can see February 11th, 2021 is the next time the next webinar is coming up. And then there are links to view all of the past webinars. Jacob mentioned our discussion forum. It's a fun place to check out. There are examples here, but there's also a webinar topic. Again, this repeats the same information. There is the upcoming schedule, and then there are links to the past recordings. And then finally, Delta has a YouTube channel. It's Delta Motion Control, all one word. You can see it there. And if you visit us there, we also have the videos. We also have the video recordings of all of the webinar links. Thanks again for your time today, and have a great day.